So thank you everyone for inviting me, and sorry for this trouble. So it is not full screen mode, but hopefully things will be visible. All right, so my today's talk is k-means clustering using random matrix sparsification. And I'll start with what clustering is. So clustering is an unsupervised learning problem. So the basic problem is as follows. So let's say we have n unlabeled examples, which we have to group. And if we specify the number of groups that you want to group all these n examples together, so idea is that essentially we'll get something like this. And each of these examples, they can have different attributes or features. So you can think about each example as a vector in some appropriate d-dimensional space if there are d attributes or features. And by saying clustering, essentially what we are meaning is that a good clustering will sort of achieve the following two things. So high within cluster similarity and low intercluster similarity. So for example, if you look at this picture, all the examples which are in cluster red, all these red points should be similar in some sense, as opposed to if you take one red example and one purple, or one red and one black, and so on. So high within cluster similarity and low intercluster similarity. So there are various clustering algorithms available, among which k-means clustering is probably one of the most widely used. And it is, in fact, the top 10 most widely used data mining or machine learning algorithms. So the problem is as follows. Again, as I said, if we have, let's say, n data points, which we can consider as vectors, let's call them A1 up to AN. And our goal is to find k disjoint cluster sets C1 to Ck in such a way that each cluster will be a disjoint subset of the original endpoints. So in k-means clustering, each cluster has a representative points, which is we typically call it as centroid. So let mu I be the centroid of this cluster Ci, which is again another d-dimensional vector, which is basically representative for all the data points that corresponds to the ith cluster. Now, so the meaning of this intercluster, within cluster similarity is basically meaning that if the jth example AJ belongs to the ith cluster Ci, then it is closest to its corresponding representative point, a centroid mu I, as opposed to other centroid points from other clusters, right? So essentially, if you look at the Euclidean distance between the jth data point and the ith representative point, that will be smaller than the distance between the same data point and any other centroid from the other clusters. So therefore, if we know these centroid points, we know what those clusters are, because you can simply compute the distance and allow or allocate any point to the closest centroid. And similarly, if we know the cluster, which data points belongs to the clusters, using those data points, you can compute a centroid points. So the k-means clustering problem is as follows. So given a fixed value of k and the data points, so k-mean clustering essentially aims to find these centroid points, because as I said before, using the centroid, you can figure out what the clustering is. And they try to minimize this following optimization problem. So basically, the idea is that for each data point, it tries to assign it to the closest cluster centroid. And the idea is to find those centroid in such a way that this, the square distance, sum of the square distance is minimized. Now, unfortunately, finding this, the optimal solution, let's call them mu1 star, mu k star, that minimizes this optimization problem is known to be NP-hard problem. So there is no polynomial time algorithm exists which gives you the exact solution, but there are fortunately very simple heuristics to solve this problem. So one of the widely used heuristics was developed by Lloyd back in 1982, and the Lloyd's heuristic simply works as follows. So it's an iterative algorithm. So you start with iteration number 1. You randomly initialize the k centroid points corresponding to the k different clusters that you are looking for, and the goal is that in each iteration you'll try to improve the centroid points so that when the algorithm stops, you'll have a very good estimate of these different cluster centroid points. So then it's basically a repeat until convergence kind of stuff, which is the standard iterative algorithm. So once we have guessed or assumed some of these initial cluster centers, we assign each of the data point to each of the cluster center which is closest, and that gives rise to the different cluster setting, because we know which clusters are being assigned to which data points are being assigned to which clusters. Based on those new clusters, you can compute the new centroid points, let's call them eta, and then we increase the iteration number, assign the new centroids to be the centroid for the next iteration, and we basically repeat this process until convergence, and then we return this, the centroid points, which are the centroids of the representative clusters. So the algorithm stops either when it reached a pre-specified number of iterations that one can specify beforehand, or if two successive iterations, if you see that either these centroids are very close or there is not much difference in the objective function, that point someone stops. Now, it is very clear that the per iteration running time for Lloyd's heuristic is of the order of n times k times d. And this is because in each iteration, the Euclidean distance from each of the k centroids of each of the n data points needs to be computed. So if the initial random choices of the k centroids are bad, because remember the first step, we are initializing the different sort of starting points, so the centroids, and which often happens, especially in a very, very high dimensional data set, it requires large number of iterations to converge. And for large data, especially in big data applications where n and d can be large, that means you have a lot of data points and your d can be very large, meaning that number of features or attributes can be very large. Again, Lloyd heuristic takes a long time because it's essentially, of the order of n times k times d. So the question is that, is it possible to make this Lloyd heuristic fast, because it works really well in applications, the goal is to reduce the computation time without significantly sacrificing the accuracy of the k-mean clustering. And over the years, there are many sort of work along that direction, that is to reduce the computation time without sacrificing the accuracy too much or the cluster quality too much. Many of these works have some provable guarantees, and they typically can be classified into two different groups. So one type of work basically tries to do some sort of dimension reduction based techniques. So, techniques that comes under this approach will be like singular value decomposition, random projection, or random column subset selection, and so on. So that here the idea is that this is our original data matrix, n times d. That means each row corresponds to a data point with d different attributes. And the idea is that we'll multiply that by an appropriate projection matrix, let's call it R, which can be d times d prime, so that the resulting matrix becomes, let's call it A prime, n times d prime. So now it has the same number of rows, but the number of columns is d prime. And typically d prime is much, much smaller than d. So the idea is that instead of performing the k-means clustering on the original algorithm, now we'll perform the k-means clustering on this, the kind of newer data matrix A prime, which has much smaller number of columns. So remember the time complexity is of the order of n times k times d. So now d is d prime. So it basically saves you some time. So the other approach is typically a coarset construction, which tries to sort of weight the different rows in such a way that the original data matrix again is n times d, n data examples. Each example has n attributes, but it tries to find a smaller subset and appropriately weighting them. It becomes n prime times d, same number of columns, but now the number of data points are much smaller. And again, instead of performing the k-means clustering on the original algorithm, on the original data matrix, now I'll perform on A prime. So the per iteration cost is now n times k times n prime times k times d, and typically n prime is much smaller than n. So again, we get a computational saving. So now in this talk, I'll talk about yet another approach, which is called random matrix sparsification. And the basic idea is to construct a new matrix, let's call it A tilde, which is of the same size, n times d, same number of rows, same number of columns, but we can randomly setting many of the entries to 0. Okay, so now we perform the k-means clustering on this sort of new sparsified sort of matrix. So first of all, why can this even be helpful? Well, so if you think that whenever you are doing this, point-wise or pair-wise distance calculation between, let's say, point AJ and a centroid I, essentially the square of the Euclidean distance, we can write it something like this. So it's the square of the norm of the data point and the square of the norm of this the centroid, and it's minus 2 times the inner product. Now, if you look at this expression, the first expression, the square of the norm of the data point, it remains the same. It's just a constant. So you can do it one time and then you are done. Now, this quantity, the norm, square norm of this, the centroid, that is constant over a single iteration, right? Iteration to iteration that can change, but in a single iteration that is sort of constant. And the third term, this inner product term, is the one that we have to continuously sort of compute for every single data point and centroid pairs. So to compute the square distance, essentially that means this quantity is the most computationally intensive. And if you sort of try to write all these data points in the form of a row of a matrix and then multiply by this vector, essentially it's just a matrix vector multiplication. Now, typically the computation time for this one is of the order of nd, because A has n rows, d columns, and mu I has d columns. And the idea is that somehow if you can make A very sparse, so that the AU computation time will be essentially of the order of number of non-zero entries in the A, right? Where, so the idea is that if you can make it really, really sparse, then you can sort of speed up this thing. So the high level idea is as follows. So we have, so in the top row, what we are showing is that let's say we have an original data matrix, which is a very, very kind of dense matrix. And what we are proposing, showing in this picture is that in the top picture over here, the gray ones corresponds to non-zero entry in the data matrix, and the white ones meaning that those are zeros. So by random matrix sparsification, we keep the same number of rows and columns, but some of the entries we make it zero. So now this data matrix looks very, very sparse, and then you perform the k-means clustering on this sparse data matrix. That is one situation where you can apply. The other situation is that original high dimensional data can be very sparse to begin with, and that is typically true if you have, like text data, right, where you represent those in the bag of word format and so on. But typically for such high dimensional data, people don't typically use k-means clustering as it is. Typically they'll do some sort of dimensional reduction step, and any dimensional reduction step typically is a linear combination of the columns. So after performing a random projection or any dimensional reduction step, it becomes a dense matrix, right? And then on that dense matrix, even we can perform this sparsification step as an additional step and perform k-means clustering over there. Right? So that is sort of the scenario where this approach that you're proposing can be applied. So the proposed algorithm is sort of very straightforward. We have a data matrix n times d. We have number of clusters that you are looking for as an input, and we have a positive scalar p that will describe in a detail. It basically kind of quantifies how many entries we want to make it to zero. And then let's say we have a gamma approximation of the k-means algorithm. Remember, k-means algorithm is an NP-hard. So whatever standard technique you use, you get kind of an approximate sort of optimal solution. So then the basic steps is, given this random data matrix, depending on the scalar parameter, we make a sparsified version of this matrix A tilde and run this gamma approximation k-means clustering that we have on the sparsified matrix and simply return the result. Okay, so that is sort of very simple algorithm. Now, there are a couple of key questions. So first of all, how do you enforce sparsification? How do you decide which entries to make it to zero, which entries to keep it as it is? And why does this sparse data matrix after this sparsification step is expected to provide reasonable k-means clustering solution at all? And finally, how do you quantify the effect of the amount of sparsity on the k-means clustering quality, right? Because at the end, that is what we sort of care about. So now, before we answer these questions, we'll sort of digress a little bit and first try to identify some essential structural information of the data matrix that kind of ensures a good k-means clustering solution. The reason we are taking this a little bit roundabout digressing route is because this will allow us to quantify to what extent the same essential structural information that guarantees a good clustering solution is preserved even after doing the sparsification, right? And in some sense, we sort of try to quantify how much sparsification is kind of necessary to make sure that we have this essential structural information preserved even in the sparsified matrix. Okay, so all right, so we have this data matrix containing all these n different vectors. And remember, we specified how each of these clusters are decided. So basically, if AJ belongs to the kth cluster, it should be closest to its centroid as opposed to the other centroid. So let's denote C of ij to be the cluster index of the AJ that is assigned. So that means if C of AJ equal to Y, essentially you are saying AJ is being assigned to the ith cluster Ci. So with this notation, it is easy to show that the cluster objective function that we introduced over here can also be written as, as this quantity, that is, square norm of AJ minus mu of Cij, and then sum over all these data points. Now we'll do a little bit more. So for any clustering, let's say C1 to Ck, there are K clusters that you're looking for. We can define a matrix called Xc, which is essentially n times K matrix. So n is number of data points and K is the number of clusters. And we define it as follows. So Xc of the ijth entry is defined as 1 over square root of Cj. That means how many entries have been assigned to the jth cluster. So that will be the jth column entry for the ith row, and otherwise it will be 0. So essentially, you can visualize this as each column corresponds to that. So if you take the jth column, it corresponds to that which of the n entries are assigned to those cluster. Those corresponding entries will have a fixed value, which is 1 over square root of Cj. All other entries will have 0. So the reason that we are trying to introduce this is that now if you look at this quantity, xc times xc transpose times A, then this matrix has the ith row equal to explicitly mu of Cai. And that means that K clustering now can be rewritten as, it's a square Frobenius norm of this matrix, which is A minus xc times xc transpose times A. Now, Xc has a disjoint support because any point can be assigned to only one cluster. We are looking for disjoint clustering. So so that means if you look at any column, any row of this matrix Xc, only one entry of that row will be non-zero. Everything else will be 0, depending on which cluster that point have been assigned to. And Xc times Xc transpose is an orthogonal projection matrix of rank A. So this projection matrix essentially projects an input matrix into a subspace spanned by the columns of this, this matrix Xc. So therefore, K-means clustering is simply a constrained low-rank approximation problem of the following form, where we try to find a, sort of all projection matrices such that A minus P times A square Frobenius norm will be minimized, where P is essentially nothing but a orthogonal projection matrix from a set of orthogonal projection matrix S. And we, so here's the catch, that S will be set of all possible cluster projection matrices of a specified form of the type SC times XC times XC transpose, because remember the form is required because at the end we want to get back a clustering solution, right? We don't want to assign each point to more than one cluster. So typically where the goal of clustering is well approximated, that is each row as close as the the corresponding cluster center is, then the objective function will be minimized. That is the standard notion of K-means clustering when a better case can be achieved. But this new formulation actually shows that the K-means problem actually amounts to finding the optimal rank K subspace for approximating the column of this data matrix A. And the choice of subspace is constrained because it must be spanned by the column of the cluster indicator matrix, so that at the end, once we have a solution, we get back a valid clustering. Now, one more thing that we'll introduce, which will be sort of required for our analysis, which is called the projection cost preserving sketch, and it is defined as follows. So let's say B is a matrix, which is n times d prime, n columns, d prime number of rows, n number of rows and d prime number of columns, is called a rank A projection cost preserving sketch of another matrix A, n times d, with error epsilon in the range 0 to 1, if for all rank A orthogonal projection matrices P of the type n times n, the following quantity holds, right? So essentially, it holds for some non-positive, non-negative constant C, and that may depend on the A and B, but does not depend on the projection matrices P. So, I mean, that is well and fine, but why do we even care for this kind of definition? Well, here's the reason. So remember the way we have constructed this definition of this, the objective function of this K-mean clustering. Now, with this definition, the implications are as follows. So if PB is the optimal solution that minimizes this quantity, B minus P times B, remember P is an orthogonal sort of projection matrix. So we are minimizing over choices of P, and P sub B is the one that minimizes this quantity. And similarly, if P sub A is the one that minimizes this quantity, A minus P sub A, again, P is variable here, then these two quantities are kind of related. So A minus PB times A, square Frobenius norm is less than 1 plus epsilon of this square Frobenius norm of this term. So what that means is essentially with this new formulation of this k-means clustering objective function, it means that if we restrict the projection matrix to be cluster indicator matrices, then optimal k-mean clustering solution of the data matrix B is in fact 1 plus epsilon optimal k-mean solution of this A. Right? So that way, with this new notation, we can sort of kind of relate the optimal solution of one clustering matrix B to another optimal solution of another clustering matrix A, and that information we'll sort of use in our analysis. Okay, so now let's give a fun fact. So the projection cost preserving sketch using the singular singular value decomposition is as follows. So let's say for the given data matrix, A sub M is the best rank M approximation of A, constructed using the top M singular vectors and the corresponding left and right singular values of this data matrix. So using basic linear algebra, we know that M can be written as sum of sigma I, Ui, Vi, where sigma I and Ui and Vi corresponding to the largest M singular values and corresponding left and right singular vectors. So it is known fact that if you choose M to be K over epsilon, remember K is the number of clusters that you are looking for, then A sub M is a rank K projection cost preserving sketch of A with error epsilon. So that means we can simply choose A sub M instead of A and perform our k-means clustering, and the solution that we can get is going to be up to 1 plus epsilon of the optimal solution of the original data matrix. So that is the kind of implication, that is optimal k-means clustering solution of AM is within 1 plus epsilon optimal k-means clustering solution of A, and the top K singular vectors and the singular values of A essentially contains the essential structural information that preserves this k-mean clustering. So when you try to sort of relate the original data matrix and the sparse data matrix, this information will sort of try to capture. So the idea is that our original data matrix A and the sparsified version can look very, very different in the outset. But the idea is that we'll try to find an appropriate lower dimensional subspace representation M prime, which is a function of K and epsilon, such that in the lower dimensional representations are kind of very, very similar, so that the essential structural information is preserved, even though A and A prime might look very, very different on the outset because of the sparsification, but essential structural information are preserved, so their clusterings will be kind of related. So now our goal is to quantify what type and how much sparsification allows us to achieve this goal, so that the lower dimension of this, this matrix, this eigenvalue structure, or the structural information will be preserved. There are two ways we can do this sampling. One way to do is that simply we can do uniform sampling. So with a fixed probability P, we select the ijth entry and keep it to be, scale it to be 1 minus P over the original entry, and with probability 1 minute P, we make it 0. Right? So essentially that means only P fraction of the entries will be non-zero. It can easily be shown that the on expectation, this is same as the data matrix, and in fact the difference between the sparsified version and the original matrix, this matrix, the largest sort of eigenvalue or the singular value is kind of maintained, which is kind of a known result, which shows that the largest eigenvalue is kind of maintained. I mean, that is important because we don't want the difference to be so huge that the corresponding eigenvalues blow up, and there is no way we can relate these two things. The other option is that we can do a non-uniform sampling, because remember, in the uniform sampling, we are not using any information about the individual coordinate entries of the data point. We are simply fixing a probability and either keeping that entry or simply just making it 0. Now, we can be smart about it, and we can do some sort of non-uniform sampling where we can decide this probability, which can be roughly proportional to the square of this that particular data matrix entries value. So if B is the largest entry, so this matrix can be roughly, the ratio of the largest, the data matrix entry divided by the largest entry and square of that. And for some analysis purpose, we sort of need to do it, sort of modify this a little bit later. And in a high level, I'll explain in a bit why we need to do that. But then essentially idea is the same. Once we have defined a new sort of non-uniform probability for each data point in a different way. So unlike uniform sort of probability that we did before, which is P is constant for all entries, ijth entries of all these individual coordinate entries of the data points. Now this thing will depend on the ijth entry of the data matrix. And again, with probability Pij, we keep the ijth entry and just scale it, multiply by 1 over Pij, or we make it 0. Right? And again, on expectation is the same matrix. And again, you can show that the norms are actually bounded of the difference matrix. So the main difference between the uniform and non-uniform sampling is as follows. In uniform sampling, we sample each ijth entry with equal or uniform probability without taking into account what the actual values are. In non-uniform sampling, we emphasize the actual value of the Aij and sample roughly each entry Aij with probability which is proportional to Aij divided by the largest entry of the data matrix and square of that. And this introduces more sparsity because we are taking the value into consideration. So we have less number of non-zero entries and compared to the uniform sampling. Now, in particular, so Aij can be very, very small. And then Pij will be really, really small. But remember, we are doing kind of a random way of choosing these entries. So even the Pij can be very, very small for an entry of this data matrix, where A sub Aij is very small, still there's a tiny probability that we might actually choose this element. And remember, we are basically scaling it by 1 over Pij. So when Pij is very, very small, 1 over Pij is even larger. So that means this quantity will be really, really large. So to make sure that does not happen, we essentially want to keep that to be, instead of squaring it, we just keep it to be the absolute value of that. And that is precisely what we are doing it over here. So that is why you have the square root of term. So it's basically square root of, the square is basically becomes the absolute value. Okay, so now our main technical contribution is as follows. So first, we show that the optimal k-means clustering solution of the sparsified matrix is approximately optimal k-mean clustering solution of its best rank M prime k approximations. And then we show that, in fact, this best rank M prime approximation of the sparsified matrix is actually a k projection cost preserving sketch of A, which means that the optimal k-mean clustering solution of this best rank M prime approximation of the square matrix is kind of close to the actual optimal solution of the A. So together these two facts implies that the optimal k-means clustering solution of A tilde is approximately optimal solution for A. So if you try to put it in a picture, it looks like, so on one extreme, we have the sparsified matrix that we are getting after sparsification. On the other hand, you have the original matrix. This looks very, very different on the outset because, this matrix has many of these entries are zeroed out. But what we are essentially showing is that some quantity, some structural information quantity in between. And remember, this is all you need only for the analysis purpose to show that these two are related. For actual algorithm, we don't need it. So what we show from here to here, how these two are connected, is that the optimal k-mean clustering of this left-hand side matrix A tilde is approximately optimal k-means clustering solution for its best M prime rank approximation. So that way, the first leftmost and the middle matrices are related. Their solutions cluster qualities are related. And then we show that this best M prime rank approximation of A tilde, this A tilde M prime sub M prime, is a rank K projection cost preserving sketch of the original data matrix. I mean, it's obvious that this is going to be a rank K projection of this A tilde, but what we show is that this, in fact, is also an optimal rank K projection matrix for this original matrix. So that way, the solution that you get over here in the middle matrix is kind of related to the left matrix. So again, so we are basically showing how the solution of the left matrix is connected to the middle matrix, and then finally how the solution of the middle matrix is connected to the right matrix. Together, we are basically showing how the solution of the left matrix is connected to the solution of the right matrix, right? And that in order to do that, we need this rank preserving cost, and we need the structural information of this singular value structure of this matrix. And essentially, we are basically quantifying how much we need to make sparsification so that that essential structural information between A tilde and A is kind of preserved, even though they look very, very different on the outside. So the very informal version of our result can be interpreted as follows. So under mild condition, a dense matrix A can be randomly sparsified to a data matrix, A tilde, such that A tilde contains, nk divided by epsilon to the n plus d times log to the 4n non-zero entries in expectation, and any k in solution of this matrix is going to be roughly 1 plus epsilon approximation factor of A. So essentially, if you think about epsilon as a constant, then essentially you have nk plus d times log polylog n factor. So if d is very, very large, then essentially this can save you a lot of time. And these are basically the main sort of more formal kind of results. So the basic, I'll not go into details, but the basic idea is that since k-means clustering is kind of NP hard problem, if you have a solution that gives you a gamma approximate solution for your original data matrix, and after sparsification, if you run that gamma optimal solution of the k-means clustering on the sparsified matrix, the solution that you get, let's call it p hat, that p hat essentially will have one additional gamma times 1 plus epsilon or time approximation factor corresponding to the optimal solution of the original data matrix. Right? So that way it kind of quantifies how much sparsification is necessary to have certain level of optimality in terms of this objective function values. So, so then I'll try to provide some empirical evaluation data sets. So we have performed this on 3 real-world data sets. One is the USPS. This is a very standard data set in machine learning. It contains the handwritten digit data sets. So each digit is 16 by 16 image presented as a vector length of 256. We seek to have 10 clusters corresponding to 1 corresponding to each digit 0 to 9. And RCV1 is one text data set. It has different news articles into 53 categories. And this is a very high dimensional data set with bag of word format. Each feature vector is of the length of 47,236. We seek 53 cluster to be the number of clusters, 1 per category. And TD2 is another sort of the text document from 30 different categories. Again, it has a very high dimensional 36,771 feature vector length, and we seek 30 different clusters corresponding to each different category. Now, USPS is pretty dense, so we keep the data set as it is. RCV1 and TD2, those are basically very, very sparse data sets. So you first perform a dimension reduction step and reduce the dimension to be 1,000 in both cases. So then after that, it becomes a dense matrix, and we perform after our algorithm on these dense matrices itself. So so we vary the parameter p from 0.01 to 1. So it basically says that how much sort of quantity we are sparsification we are allowing. So q represent the fraction of the entries in the sparsified matrix, which is 0. In case of non-uniform sampling, q equal to p, because that is precisely how much entries we are making it to 0. For non-uniform sampling is typically much smaller, and this curve corresponds to that. In the x-axis we have p and y-axis we have q. So as you can see that the p, the parameter, as we are increasing for larger values, we have it basically zeroes out more number of examples correspond to the uniform sampling. Now we perform our k-mean clustering algorithm on 3 different data sets 30 times, every time initializing with the k-mean plus sort of initialization, and taking the best solution out of those 30 as the objective function values and the corresponding clustering. So we define Lx to be the cluster indicator matrix obtained from the k-means clustering result on the original data matrix, and let's xq be the clustering indicator matrix obtained from the k-means clustering applied on the sparsified matrix with q fraction of the entries set to 0. And these are the 3 different empirical quantities that we are trying to sort of compare. So one is H1 of Q is basically ratio of these 2 quantities. So the numerator essentially corresponds to, if you remember the alternate formulation of the k-means clustering, it is nothing but the objective function that we get for the sparsified matrix. And the bottom we have the objective function, k-means objective function that we get for this original data matrix. And the idea is that we'd like to have it very, very close to 1, right? The closer the 1 it is, the better. H2Q measure the normalized mutual information. So that is one metric typically people use to find what is the cluster quality. And the higher the values, the better. And then finally, also we do another H3 of Q, which is simply, this is the normalized objective value. So basically this is the objective value, which can be very large. So you normalize by the square Frobenius norm of the matrix to make sure that it does not sort of becomes too large. And essentially the faster this quantity decreases, the better. So here are some of the results. So each column corresponds to 3 different data sets. This is USPS, TDT2, RCB1. So this is for the first matrix H1Q. Remember, this close to 1 is better. This is the corresponding for the mutually normalized mutual information, or NMF quantity that quantifies the quality of the cluster. And this is basically the normalized objective function. So again, the smaller the better. So the two things to observe here. First of all, the unnormal, so the non-uniform sampling, which is shown by the blue line, which kind of works well compared to the uniform sampling, and which is kind of expected because in the uniform sampling, we are simply zeroing out the quantities without paying any attention to their actual values. But in the non-uniform sampling, we are kind of selectively choosing values, which entries to keep, considering with the actual square of the values. So clearly, the non-uniform version actually make things zero quickly quite fast, and it actually gives you much better result compared to the uniform version. But the main thing to notice here is that for the H1, which is the, remember we have this 1 plus epsilon approximation guarantee, and as you can see that very quickly as you increase Q, the ratio becomes very close to 1. This is the 1, again, this is the 1 here, and this is the 1 here. So very quickly it kind of goes to close to 1, meaning that it kind of agrees with the theoretical results that the k-means objective function becomes kind of 1 plus epsilon approximation factor as you slowly increase then how many entries are becoming 0 and so on. So in some sense, this kind of agrees with the theoretical results that we have. So to conclude, we present the first theoretical result that shows how random sparsification can be used to speed up the k-means clustering computation time, ensuring the 1 plus approximation guarantee. Our proposed approach provides additional computation speedup in addition to what can be obtained by dimension reduction and core set construction. So remember, this is basically, you can do your standard dimension reduction technique, which will give you some computational speedup or core set construction. On top of that, if your matrix is still dense, on top of that, you can apply this matrix that is sparsifying even more and can get additional sort of speedup or computational speedup. So empirical evaluation on 3 different real-world data sets show strong agreement with our theoretical results. Now, before we kind of conclude, I just want to give you a very high-level idea, some of the current and future work that we are doing in your lab here. So this can be roughly classified into different categories. So from theoretical to semi-theoretical to applied. So on the theoretical side, we have a new grant of NSF-AI Institute with collaborating with UT Austin, University of Washington, and Microsoft Research. And our focus is to sort of learn various foundational problems, especially connected to deep learning. And for the next 1.5 years and so, our focus is to understand the role of over-parameterization in neural networks, because in recent years, it has been observed that over-parameterized neural network works really, really well, but they have, the amazing kind of, ability that even random label noise, they can fit it very well. So that means they can have absolutely zero random noise, but then they perform very bad on the test data set. Whereas for the regular data set, it performs really well. So we're sort of trying to understand that what is the role of over-parameterization is in neural network and its connection to robustness and generalization. So this is kind of still not very well understood, and we hope to make some kind of contribution in this field towards that direction. In the semi-theoretical direction, so I have collaborators from IBM Research where we are looking at a couple of problems. One is we are currently working on is on gradient-free neural neighbor encoding scheme. So this technique is essentially inspired by how the fruit flies olfactory design works. And essentially, this is a very, very cheap kind of computational sort of process in the sense that all we need is this addition-only operation. And that can sort of, give you kind of very nice way of encoding sort of the neighborhood in high dimensional data space, which can later be used for designing different classification algorithm. And by the design, we suspect that it has some connection to differential privacy in the sense that maybe it provides differential privacy for free and may have some robustness against the adversarial perturbation. So we are basically studying those kind of properties along with my IBM research collaborators. Another problem that you're working on is study of various consistency property of classification scheme using something called a random projection trees. So the random projection trees is a kind of random data structure that have been used and shown to be used very well for nearest neighbor search, but we are trying to use that in the classification setting. And an ensemble of this random projection trees, we suspect that it might have some nice consistency properties similar to the random forest that we typically use. And that is one direction that we are trying to working on right now. On the applied side, we have a couple of things going on. We recently have a funding from the state of Kansas for creation of a data-enabled disaster resiliency analytics center, or DRAC, at Wichita State. And the goals are typically to improve our ability to predict natural disasters before using multimodal data such as meteorological data, such probably social media data, CubeSat imagery, and so on, and also to improve the community's preparedness and ability to respond after the disaster strikes. So it's kind of a resiliency kind of prediction based on the economic data, the poverty, the income of different communities, and so on. So that is something that we have kind of next 3 years a grant we are working on that project. Another applied project that we have been working on is in the clinical setting, healthcare setting, collaborating with a couple of physicians. The idea is to application of deep learning techniques to solve various clinical and health research problems. So essentially, we are trying to do in the ICU setting. We have, for the different patients, we have their vitals data, their labs data, their doctor's notes, nurses' notes. We have different image type data like CT scan, MRI, X-rays, and so on. So the idea is that using all this data, and essentially in ICU, we have all these labs or vital measurements over time. So those are kind of time series data. And we are trying to use different deep learning techniques like LSTM, like long short-term memory model, GRU, and especially the attention mechanism. And we are trying to sort of use all these, deep learning advanced models into this healthcare or clinical setting. For example, to do disease onset prediction, right? Can you predict 4 hours before actually the onset so that a physician can intervene and maybe take some actions. Also for ICU length of stay prediction, because that might be really helpful to manage the resources of ICUs like beds and ventilators and other stuff. So those are the kind of another applied work that we have been doing. So the basic idea is, again, there's nothing fancy here, but use advanced deep learning techniques to solve various clinical or healthcare setting problems. So those are, kind of very high level, some of the research efforts that we are going on currently. And thank you so much for your time. And if you have any questions, I'll be very happy to take those.
Thank you, Kaushik. That was a great talk, great summary, and a pretty cool technique. So the floor is open for questions. You can either submit in the chat or you could speak up. I think while we are waiting, or actually there's a question here, sorry, from Anurag. You want to ask, Anurag?
Yeah. Hello. So here I have a question. Like when you're using random projection for the inputs, right? So you're basically trying to lift it, right? You're basically trying to increase the dimensionality for the inputs at that point of time, right? Making it.
No. So the basic random projection is that you decrease the dimensionality.
But
right?
Yeah, but in the for like network diagram which you showed, it seemed like you're increasing the dimensionality and then sparsifying it.
No, so that sorry. So that is a different work. So we have this neural embedding. So that is a different kind of work. So this is something different. In traditional sort of random projection, you have this famous Johnson-Lindenstrass theorem. It essentially tells you that, well, if you have an n by d data matrix, if you randomly project onto let's say log n over epsilon squared, that many dimension. So then you can have all the pairwise distances of points can be preserved up to 1 plus minus epsilon. So remember that you can have 1 billion points or even 1 trillion points, right? But it does not depend the dimension that you want to project to using random projection, so that all pairwise distances will be preserved roughly depends on the log n of the number of data points, right? So essentially you are trying to, so that is how the random projection typically is used as a dimension reduction step. But what you are talking about is a kind of a different set of works that we are, it's a different kind of work that we are doing for in the classification setting, where you are basically lifting it up. But the traditional use of random projection is always used for dimension reduction. So as long as you have roughly log n number of random projection direction where you can project to, pairwise distances are kind of preserved.
Okay. So here, like I have a follow-up here, like when you have these, okay, when you're projecting it, and then like I don't see the intuition behind like why you then sparsifying it. If you're lifting it and then sparsifying it, it like that way, like the features will still be there, or the information gets more distributed in that context. But how does sparsifying it after projecting help? Or
no,
unless
so, okay. No, so okay. So remember, the sparsification step is not necessary for this technique. So there are two situations where you can apply this technique, right? So if your original data matrix is already sparse, then you can use it as it is. But if it is, but the basic idea of the random projection step is that you want to dimension, sort of reduce the dimension in such a way that your pairwise distances are still kind of preserved. So you are not losing too much, right? But then once you're reducing the dimension, you are basically gaining something, because now each data point can be represented by a much fewer number of attributes. So when you do the pairwise computation, distance computation, you are basically gaining. You have to do less computation. What you are suggesting is that even in that case, if you do a sparsification, that means even if you do even less computation. Right? Because whenever, so think about this, if you have a matrix, so if let's say you are doing an inner product between two vectors, if there are D entries, then essentially you need to multiply pairwise each of these coordinates, add those up. Roughly, this is of the order of D. But if there are only, let's say, fixed number of non-zero entries, you need to multiply only those non-zero entries and those add those up, because everything which is zero, they're not going to contribute anything, right? So that way you are basically gaining, saving some kind of computation.
Yeah, we are saving computation, but like aren't we losing on the information from each data point which we have?
Yes, so but that is so
if
that
the data set increases or it has like very closely related samples.
Right, but that is the whole idea of this 1 plus epsilon approximation guarantee, is precisely ensures that how much you can sparsify so that you do not need lose the essential structural information, so that at the end, even though the sparsified matrix and the original data matrix looks very, very different, but still the k-means the optimal objective function of the original matrix and the data matrix are still kind of close. So this work basically tries to tie down these two kind of different notions, that how much you can sparsify, still we can guaranteeing that their kind of optimal solutions are going to be close, at least within 1 plus epsilon factor.
Okay.
Right. So that basically kind of quantifying that how much sparsification is kind of required still to ensure that their optimal functions are within 1 plus epsilon approximation factor.
Okay. Okay. Thank you.
Yeah.
Thanks a lot.
Other questions? Okay, I think while people are... Sorry, I muted myself. I think in following up with Anurag's question, right? So your goal seems to be in trying to get this sparsification and then doing that k-means clustering is to speed up the computation.
Right.
But there is like a threshold on how much you're going to be able to sparsify.
Right.
Right. So I've seen that you've done this theoretical analysis with these 3 data sets.
Right.
But did you kind of computationally see what is the limit or like what is that upper bound for the different types of data sets out there? I know you're more on the theoretical side, but I'm just like coming in from the ML side. It would be interesting to see. And also, I think your application of this technique in 2 scenarios, right? So depending on what kind of dimensionality reduction I would use on the front end, what would the impact be, or what would be the limit be on that kind of threshold? I thought that would be interesting from the ML side.
That is actually a very great question. And no, unfortunately, we haven't done that, because the main motivation of this was kind of understanding this, to sort of quantify that, first of all, whether at all it can be beneficial, and if it can be beneficial, how to sort of quantify. But that is definitely a very good question, and that is definitely we'll sort of try to look it up in the future.
And
thank you. That's a very great question.
Okay, and the other follow-up to that, or maybe like we work on the a different kind of, it's called random projection, but in this case, like what Anurag is asking, we kind of lift up, right? We kind of take the data and lift it up to a higher dimensional space.
Right.
And in those cases, maybe we can use, and we have done some sparsification after that.
Okay.
So in those scenarios, how do you think intuitionally, I mean, it's how would this technique work? Because in your scenario, you're kind of reducing the dimension, and because it's a dense matrix, there's an opportunity to sparsify it when you reduce the dimension, and then you can perform this k-means clustering on that.
Right.
So what do you think would happen if it's the other case where you're kind of lifting up the data and then performing those steps?
Well, so we have some work in that direction as well. For example, there is a kind of a very interesting, Nature or Science paper, I believe. So they pretty much try to do the same thing, what you were suggesting. So you lift it up using random projection. And even their random projection construction is even much simpler. So you don't have to use this, Gaussian 0+ entries. It's just 0, 1 random matrices. So it's kind of addition only operation. And then once you get a high dimensional projection, you kind of take it, not take it all. So just keep the largest k values to non-zero and everything else to 0, right? You can show that in certain structural assumptions, the pairwise distances are still preserved. Right. And then you can do something with that kind of very sparsified structure, because still it kind of maintains the pairwise distances. So essentially not everything is lost, but then this sparsified version you can sort of utilize towards your kind of benefit towards developing different algorithms. So so what I'll suggest, in this setting, what essentially, if it is very sparse, essentially remember the way we constructed this problem is that this pairwise distances essentially relies on this inner product. Inner product depends on how many number of non-zero entries you have. So even after lifting it up, after making sparsifying, how many non-zero entries you have in this data matrix representation, that will essentially guide your computation time.
Okay, very interesting. I look forward to having discussions offline further on this. Before we wrap up, any other questions from the group? Okay. Tulio, did you have a question?
No, I was going to answer no. You asked a question and there's a silent room, so I just wanted as a coordinator to say no.
Okay, thank you so much, Kaushik, for taking time to present about your research, and all the best with the NSF AI Institute, and look forward to having further discussions with you.
Thank you so much, and thank you for inviting me. It was a great pleasure. Thank you.
Thank you.
Have a good day. Bye-bye.
Yeah, you too. Anyway, thank you, everyone.